The last part of section 6.5 is called the Logistic Growth Model. And the Logistic Growth Model is this differential equation, change in population with respect to time. And when we talk about this change in population with respect to time, the relationship is some constant over m times p, m minus p. M stands for the maximum carrying capacity, or the amount that the environment is capable of sustaining. So if it goes over that m value, then that's when overpopulation happens and animals start kind of dying off because of overpopulation. P represents our population, and K is our proportionality constant that is always positive. Now, a lot of times you're going to see this written in a way like K over M, and then PM minus P squared. You'll see it in a bunch of different types of ways where they've distributed it out, but this is the most common way to see it. And so here it does say if the population were to exceed that maximum carrying capacity, then the growth rate would be negative and the population is decreasing. Now, they tell you the solution to this problem, which means if I anti-derived this, if I moved my dt over and I moved my p's over and they did all of the antiderivative work for you, this is the equation that they come up with. You don't have to prove it or anything, but this is the equation, this is the derivative of this equation. So this is that solution. A, this value A right here, is determined by the initial condition. I want to note that A is not the initial condition. It's determined by the initial condition. The initial condition is going to be some sort of ordered pair, like 0, 3. This is your time, this is your population. So T and P are your initial condition, and you're going to solve for A. So example 4 says we have the growth rate of a population of bears in a newly established wildlife preserve, and it's being modeled by this equation. So here's my K over M, P, M minus P, where T is measured in years. And so I would even write that right underneath here. So now part A says, what's the carrying capacity for the bears? Well, if I go back up here, M is my carrying capacity, and I can see right here that M is 100 bears. And so then it says, what is the bear population when the population is growing the fastest? So they are asking us here, what is the maximum of dp/dt? So I want you to take a second and graph dp/dt and try to find the maximum. Go ahead and put it on your graphing calculator and find the maximum of this function. It's a quadratic. Now, because that formula is a quadratic, that means that that function is symmetric. So the maximum you should have found was 50 bears. And the cool thing about this is because these are always going to be quadratics, when we do the distribution, we get a p squared in there. They're always parabolas that open down. The maximum is always going to happen at half of our maximum carrying capacity. So our population will always be growing the fastest at half of m. So that would make sense in this case. It was 100 bears, now it's 50. So letter C says, what is the rate of change of the population when it's growing the fastest? And when we see this phrase, rate of change of population, that's dp/dt. And it says, what is the rate of change when the population was growing the fastest? It was growing the fastest when the population was 50 bears. So we need to figure out what is dp/dt when the population was at 50. So my dp/dt equation is right up here. So 0.008 times 50 times 100 minus 50. And go ahead and put it in on your calculator. And you should end up getting 20. Now, what are the units here? And this one is always my favorite. It's bears per year, but every year I always have someone tell me that it was bears per minute, and that's just nasty. You can't have that many bears reproducing per minute. Yuck. All right, I want you to add a part D on here, and part D is, I would like you to know, what is K? And so in order to figure that one out, when we look up here, we see that K over M was 0.008. A lot of these problems will ask you to find that proportionality constant. And we know that M was 100 this time around. So when we multiply by 100, we get that K is equal to 0.8. All right, on the next page, there are two free responses. There's one up here and one down here. The video is going to show some solutions to this one, and then I want you to try the second one on your own. So go ahead and work through this first one, and then I will slowly reveal the answers on that. All right, so first thing I did was the K over M and the M, recognizing that my M in this case is 3,000. So I first need to figure out what my K is. So if I did K over 3,000 equals 0.001, we get that K equals 3. So that's going to help us out because the next one says an initial condition. And remember, this means this is T and this is P. And it says to solve for P as a function of T. So we're going to be using the equation from back here, the original equation that's in terms of P and T. So I started with P of T equals M over 1 plus A e to the negative KT. I already figured out what K was up here. We said K was 3, so I have to do negative KT in here. And now we've got this initial condition. T is 0 when P is 50. Remember, that's not our A. We're going to plug in 0 and 50. So when we plug in 0 and 50, e to the 3 times 0 is e to the 0, which is 1. So that kind of goes away. Now, I multiplied both sides by 1 plus A. So I have 50 times 1 plus A. And then divide both sides by 50. I end up with 1 plus A equals 60, so A equals 59. We've now used that initial condition to solve for A. And so the only other thing I have to do is put the A back into the original equation. So we get that lovely population equation. All right, now it says in part B to use your solution from part A to find the population at 2 days. So go ahead and do that. That was just a simple plug and chug. Put it in on your calculator, so you should get 2,617 people. And then part C says use your solution from part A to find the number of days that have occurred when the flu is spreading the fastest. So remember the hints that I told you about that. Go ahead and figure that one out. We need to remember that the flu spreads the fastest at that halfway point. So half of that carrying capacity is at 1,500. So we want to know when is the population at 1,500. I found the easiest way to do this, put this into y1 and to put this into y2 and find where those two functions cross. You have to make sure you find an appropriate window there. But I found the intersection at 1.359 days. All right, there's one more free response down here that I'd like you to work on, and we'll talk about that one in class.